Video 8. Problem number 11. Balls are tossed at random into 50 boxes. Find the expected number of tosses required to get the first ball in the fourth box. So there are 50 boxes placed. 1, 2, 3, fourth box. So like that 50 boxes are placed. So we are going to toss one ball at a time. Suppose in the first toss itself, if the ball gets into fourth box, then the game is over. So we have to repeat the toss until a ball lands in fourth box. So we need expected number of tosses required. So what is our x? Expectation of x. Let x be the number of tosses required until a ball gets into fourth box. So we have to repeat the experiment until a ball lands in the fourth box. So that is number of tosses. Then the word until is very important for geometric distribution. Then capital X is a geometric variate. What is our P? P is the probability that the ball lands in the fourth box in one attempt. So what is the probability? Because there are 50 boxes, the ball may land in one of the 50 boxes. So the probability that it lands in the fourth box is 1 out of 50. So P value is 1 by 50. For a geometric variate, expectation mean value is equal to 1 by P. We know that for a geometric variate, mean is equal to the expected value of number of tosses required is equal to 1 by P. That is 1 by P is 1 by 50, that is 50. Therefore, the expected number of tosses required to get the first ball in the fourth box is 50. So whether it is fourth box or seventh box, it is immaterial. So this number 4 is immaterial. Any one box, say either 2 or 7 or 9, any box numbered with that one. So this completes problem number 11. So we will go to now this continuous random variable problems based on continuous random variables. So far we have discussed problems on discrete random variables. Continuous random variable, problem number 12. Problem number 12 show that the function f of x is equal to e power minus x for x greater than or equal to 0, 0 for x less than 0 is a PDF. PDF means probability density function of a continuous random variable or V random variable. So there are two conditions to be satisfied for a function to represent PDF. What is the first condition? F of x must always be greater than or equal to 0. Clearly, f of x is greater than or equal to 0 for all x. If x values are negative, f of x is 0, so not negative. E power minus x is nothing but 1 by e power x. When x is positive, 1 by e power x is also positive. Therefore, f of x value never be negative. So, f of x greater than or equal to 0 for every x. So, that is the first condition. Second condition is integral minus infinity to plus infinity f of x dx must be equal to 1. So, this will have to split into minus infinity to 0 fx dx plus integral 0 to infinity fx dx. We have to split into two integrals. Here the value of x is less than 0. In this integral, x value greater than or equal to 0. So therefore, this f of x value for x less than 0, f of x is equal to 0. So first integral 0. Second integral is 0 to infinity e power minus x dx. For x greater than or equal to 0, f of x is e power minus x. E power minus x integration is e power minus x by minus 1 with the limit 0 to infinity. So upper limit is e power minus infinity by minus 1, e power minus 0 by minus 1. So e power minus x tends to 0 as x tends to infinity. That is, e power minus infinity tends to 0. Minus e power 0 is 1. 1 by minus 1 is equal to 1. So both conditions are satisfied. Therefore, the given fx is a PDF, probability density function of a continuous random variable. So this completes problem number 1, and video 8 also completed.